Metal or plastic? Which impeller is more durable, and which one really costs less? If you answer from the material name alone, you can get both questions wrong. A thin welded steel wheel, a formed aluminum wheel, and a stainless wheel do not share one performance limit. Neither do polypropylene, glass-reinforced polyamide, and high-temperature engineering polymers. The correct comparison starts with an exact material grade, an exact geometry, and an exact duty. First, map the rotating load. Every blade and side plate creates centrifugal force as speed rises. The load grows with mass, radius, and the square of rotational speed. Lower density polymers can reduce rotating mass and inertia, which may help acceleration and reduce bearing load in some designs. But density is only one term. Strength retention, fiber orientation, hub design, stress concentrations, joining method, and operating temperature decide whether the complete rotor has enough margin. That is why plastic is weak is not an engineering conclusion. A reinforced polymer can be molded into ribs, curved blades, hubs, and locating features that would require several metal operations. Integrating those features can improve part-to-part repeatability and remove some joints. But injection molding introduces its own risks: weld lines, voids, fiber orientation, moisture conditioning, dimensional change, and residual stress. The production process and tool condition are part of the material system. Temperature is the first major gate. Metals generally retain useful stiffness over a wider high-temperature range than common thermoplastics. Engineered polymers have grade-specific limits, and their stiffness, creep resistance, impact behavior, and dimensions can change with temperature, time, and moisture. A short temperature peak is not the same as continuous service for 40,000 hours. Ask for continuous use data, not only a melting point or one heat deflection number. Metal is not automatically maintenance-free. Carbon steel can corrode, aluminum can suffer in incompatible chemical or galvanic conditions. Stainless performance depends on grade and environment. Coatings help only where preparation, coverage, edges, and damage remain controlled. Plastics resist many corrosive media without a coating, but no polymer is universally chemical-proof. Cleaners, oils, refrigerants, acids, alkalis, ozone, ultraviolet light, and hot water must be checked against the exact grade at the actual concentration and temperature. Next is impact and fatigue. A metal wheel can offer high stiffness and broad size capability, yet poor forming, a sharp notch, a weak weld, or uncontrolled residual stress can become a fatigue origin. A polymer wheel can absorb some impact and avoid corrosion pits, but long-term creep, cyclic strain, molding defects, or an incompatible medium can reduce margin. Neither material deserves a durability claim until the complete rotor passes overspeed or burst validation, fatigue cycles, temperature and humidity conditioning, and the project's impact or debris test. Balance is equally non-negotiable. More mass does not automatically mean more vibration, and lower mass does not automatically mean quieter operation. Residual unbalance, eccentricity, runout, shaft fit, structural resonance, blade passing interaction, and the installed housing all matter. The appropriate balance quality and vibration limit must match the fan application. Aerodynamic noise often dominates material noise, so compare tested sound at the same operating point and installation. Now consider manufacturing and cost. Metal fabrication can avoid a large mold investment in suit low volume, large diameter, or highly customized work. But cutting, forming, welding, coating, secondary machining, and balance correction add labor and variation. Injection molding requires serious upfront tooling and process development. Once validated at sufficient volume, it can produce complex integrated geometry with short cycle time and fewer secondary operations. The crossover point depends on annual volume, tool life, cavity count, scrap, inspection, change risk, and logistics, not the price per kilogram. Use a 6-card stress test. Card 1, exact grade, reinforcement, alloy, coating, and joining process. Card 2, maximum continuous temperature, peak temperature, humidity, and thermal cycles. Card 3, every chemical, cleaning agent, condensate, salt, dust, and ultraviolet exposure. Card 4, speed range, diameter, inertia, starts and stops, overspeed margin, and containment. Card 5, balance grade, vibration, sound, fatigue, and impact validation. Card 6, tooling, unit volume, quality controls, repair strategy, recycling, and total delivered cost. The answer is therefore conditional. Choose a validated metal design when temperature, large size, structural stiffness, low volume customization, or a proven alloy and joining route creates the best margin. Choose a validated engineered polymer design when low rotating mass, corrosion behavior, integrated geometry, repeatability, or production volume creates system value. In both cases, validate the complete impeller, not a material sample. If you want one material decision reviewed, send the wheel geometry, speed, airflow duty, temperature profile, media list, annual volume, and required life. Longwell can make every assumption visible before tooling begins.